Your plant's in business to produce and sell electricity, but it also uses a lot of electricity itself. You've seen the electric motors that run plant equipment, and you know that your plant couldn't operate without its electrically powered instruments and tools. Well, you're probably familiar with some of the terms associated with the use of electricity, terms like current, watts, and volts. But if you tried to tell someone exactly what electricity is, could you do it? Well, in this unit, you're going to learn what electricity is and how it works. You'll also learn more about the terms and symbols that are used to describe electrical energy. We'll show you some formulas that you can use to figure out how much electricity you've got and some of the meters that are used to measure it. We'll be talking about DC, direct current, in this unit. We'll cover AC, alternating current, in another program. Now, since we're covering the fundamentals here, some of the ideas may be familiar to you, but don't think that they're not important or that they're too obvious to bother with. You'll need to use what we cover here as a basis for understanding what comes up next. Okay, let's start with the fact that electricity is a basic phenomenon found in nature. It's already there, in other words. Electricity is basic to all matter. And matter is anything that has mass and occupies space. Matter itself is made up of small particles called atoms that can't be seen without special equipment. Seeing them isn't really important for our purposes anyway, but understanding what an atom's made of is. Basically, an atom consists of three different types of particles called neutrons, protons, and electrons. The neutrons and the protons are located in the center, or nucleus, of the atom. And the electrons orbit around the nucleus the same way that the planets orbit around the sun. Two of the three particles that make up an atom carry a charge. They're the ones we'll be concerned with. The protons carry a positive charge, and the electrons carry a negative charge. Neutrons are different. They don't carry a charge. They're neutral particles, so neutrons aren't really important as far as electricity is concerned. Now, since the nucleus of an atom is made up of protons, which are positively charged, and neutrons, which have no charge, the nucleus of an atom always has a positive charge. This positive charge is matched by the negative charges carried by the electrons that travel around it. How these positive and negative charges interact is really what electricity is all about. As you'll see later, there are a number of things that can cause the negatively charged electrons to move. This movement or flow of electrons is electric current or electricity, the thing your plant produces. So let's concentrate on electrons and how electrons move. As we said earlier, all matter, every kind of material, is made up of atoms. So every material contains electrons. I can't show you the electrons, but I can use some common materials to show what happens when electrons move. Now, here I have a couple of glass rods, got a rubber rod, and some fabric. Now we're going to use friction to move some electrons from one item to another. I'll begin with this piece of silk and this glass rod. As I rub the silk against the glass rod, a great many electrons move away from the glass onto the silk. Now, this diagram shows what happens more clearly. Rubbing, or friction, causes the negatively charged electrons to leave their orbits around the positively charged nuclei in the atoms of the glass rod and move to the silk. This transfer of electrons gives the silk cloth a negative charge because it gained electrons. The glass must have a positive charge because it lost electrons. Now, let's use the woolen cloth, this time with the rubber rod, and repeat the procedure. Rubbing the woolen cloth against the rod transfers electrons from the wool to the rubber, in this case giving us a negatively charged rod and positively charged wool. Okay, now these charged rods can show us something about the behavior of opposite charges. Now we'll put this rubber rod in the string on this stand, make sure it's well charged, and then watch what happens when I take the glass rod that is positively charged and hold it near the rubber rod that is negatively charged. Aha, you see, the two rods move toward one another. They attract one another. Okay? Now, that's important. Keep it in mind. Opposite charges attract. Well, what happens when we put objects with the same kind of charge together? Here's another glass rod. I'm rubbing this with the silk cloth just as I did before. And we'll put this in our little stand. Make sure it's well charged. Get the other glass rod. So what we have here are two positive charges. Now, no attraction. Matter of fact, they move away from each other. Like charges repel each other. Now, these findings are important. Let's review what we just learned. Opposite charges attract, like charges repel. Positively charged objects always attract negatively charged objects and repel other positively charged objects. Now, let's get back to the flow of electrons for a minute. Like charges repel, so electrons move away from each other, the same way that the two glass rods did. On the other hand, the negatively charged electrons are attracted by the positively charged nuclei, so they move toward the nuclei. The electrons keep moving until the positive and negative charges balance out. When the positive and negative charges are equal, electrons are no longer repelled or attracted, so they stop moving. Electron flow stops when there is no longer any potential difference between positive and negative charges. I can illustrate this point with a diagram of two connected water tanks. The water flow in these tanks works just about the way electron flow does. The water levels, like electrons, continually try to equal out. The electrons move in order to eliminate the potential difference between positive and negative charges. The potential difference between the water levels in the two tanks, 4 feet of water in the tank on the left and 2 feet in the tank on the right, will also equal out. As long as there's a path for the water to flow from one tank to the other, the flow continues until the levels in the two tanks are equal. In this case, the water level is now 3 feet in each tank, and the flow stops. To sum it all up, we can say that electron flow occurs because of the potential difference between a negative charge and a positive charge. As we said earlier, the flow of electrons is called electric current. Current flows as long as there is a potential difference between a negative charge and a positive charge. Now, this battery has a positive charge here at this terminal where the plus is, and a negative charge at this terminal indicated by the minus side. Now, when this wire is connected from the negative terminal to the positive terminal, electrons begin to flow through it. By the way, this wire makes it easy for the current to flow. It's made of copper. If I used a length of rubber or a piece of string instead of the copper, I'd still have some electron flow, but so little that it would amount to almost nothing. The reason for this has to do with a property called resistance. All materials offer a certain amount of resistance to the flow of electrons, but some offer much more than others. Certain materials like copper, silver, and aluminum permit an easy flow of electrons. They offer very little resistance. Materials like these are called conductors. String and rubber, on the other hand, offer a great deal of resistance to electron flow. Materials with a great deal of resistance are called insulators. They do not permit an easy flow of electrons. Now, there's one more fact we ought to mention. Electrons must have an uninterrupted path to follow or they will not flow. Now let's look at this battery again. By hooking the wire to the positive and negative terminals of the battery, we create a complete path or circuit through which the current can flow. But if I disconnect this wire, I interrupt the circuit, and the electron flow stops. Electron flow cannot begin again until I close the circuit. An interrupted circuit is called an open circuit. A complete circuit, then, is the path beginning at the negative terminal and ending at the positive terminal of this battery. The potential difference between the negative and positive charges of the battery is called the voltage. Voltage is necessary in order for current to flow in the circuit. So, next, we'll talk about how to produce voltage. But before we get into that, why don't you take a minute to think over what we just covered and read over the material in your text. Remember, if you've got any questions, now's the time to ask your instructor about them. Let's pick up where we left off on voltage by recapping what we've already said about it. The most important fact to remember is that voltage is the potential difference between a positive charge and a negative charge. We often use numbers to discuss voltage. For instance, you refer to the battery in your car as a 12-volt battery. Volts are the units used to measure voltage. We also said you won't get current to flow without voltage, but we didn't say exactly why. Well, voltage is actually the force that causes electrons to flow. The more voltage there is, the more force there is to move those electrons along. We're going to describe 6 common ways to produce voltage. We'll cover light, pressure, heat, and friction in this segment, and chemical action and magnetism in the next. Each one of these methods involves transforming one type of energy, the energy found in heat, for example, into another type. The type we want to produce is electrical energy. The first source of electrical energy we'll look at is light. One device that transforms light energy into electrical energy is a photoelectric cell. Remote installations with no power lines going to them often use photoelectric cells to produce voltage. This voltage is stored in batteries and used to supply power to the installation at night or on cloudy days. There's a photoelectric cell on this bridge. It powers a probe that monitors the rate at which the metal in the bridge corrodes. By periodically checking how much the metal's corroded, maintenance work can be scheduled as needed to prevent a major catastrophe like a collapsed bridge. Photoelectric cells can be made of lots of different materials. The ones that are used depend on the type of light available and how much voltage is needed for a particular application. This cell has an iron base with a special alloy plate on top of it. This lens focuses light on the alloy. It works this way. When the light is focused on the cell, the light's energy causes electrons to move from the alloy into the iron base. The alloy loses electrons, so it becomes positively charged. The iron gains electrons, so it becomes negatively charged. The difference between these charges is the voltage. The more intense the light, the greater the voltage across the cell. Pressure is another source of energy that can be transformed to produce voltage. You've got pressure detectors in your plant. They're generally used to alert you to various conditions. They'll detect the amount of pressure in the various components in the steam cycle, for instance, and send out signals that'll operate meters or set off an alarm if the pressure is getting too high. The type of detector we're looking at here produces voltage by applying pressure to certain kinds of crystals. It's done this way. There's a crystal between this set of metal plates. A sensing line connects this device to the system in which pressure is being measured. Pressure from the system is applied to the crystal. The force of the pressure passes into the atoms that make up the crystal and drives the electrons out of orbit in the direction of the force. The electrons accumulate on one of the metal plates. giving it a negative charge. The amount of difference between the negatively charged plate and the other plate is the amount of voltage produced. So the voltage is proportional to the pressure that's being measured. That's why it can be used to operate meters and recorders to indicate exactly how much pressure there is in the system, or initiate alarms if an abnormal pressure occurs. Heat's the next method we'll look at. We'll use a thermocouple as an example of how energy from heat is transformed into electrical energy. Some of the machines in your plant probably have thermocouples embedded in their bearings so you can monitor their operating temperature. A thermocouple is made of two different metals joined together. In order to generate a voltage, you apply heat at the junction, here. This thermocouple is made of copper and iron. This end is called the hot junction because that's where the heat is applied. These other ends are called cold junctions. When heat is applied here at the hot junction, there's a difference in the way the metals respond. The electrons in the copper flow away from the hot junction, but the electrons in the iron do just the opposite. They flow toward the hot junction. So you end up with a negative charge at the copper terminal and a positive charge at the iron terminal. You produce a voltage by applying heat at this point. The amount of voltage you get at these terminals depends on the difference in temperature between the hot and cold junctions. The voltage produced by a thermocouple can be used to operate a meter or a recorder. That voltage is directly proportional to the temperature that the thermocouple is measuring. That's why the meter or recorder is able to indicate what the measured temperature is. Friction is the next method of producing voltage that we mentioned. Earlier, we used friction to transfer electrons from glass to silk to illustrate some basic principles of charged objects. But the kind of voltage we get as a result of friction is really more of a nuisance than anything else. Most of the time, we want to eliminate it rather than use it. Let's look at this coal conveyor belt for a minute, and I'll show you what I mean. There's friction here between the coal and the belt, and between the belt and the rollers that it passes over. As we saw earlier, when different materials rub against each other, electrons leave one material and move to the other. You remember how it works from the diagram we saw in the first segment. Well, now the kind of voltage this friction produces is called static electricity. It comes from a buildup of positive and negative charges caused by the rubbing motion. In equipment such as a conveyor system, these charges can build up enough to cause sparks, and these sparks present a problem. If they were to ignite the coal dust, you might have a first-class fire on your hands. So it's important to get rid of the static electricity before it can build up. On this conveyor, the static electricity is transferred through the metal rollers to the frame, and then from the frame into the ground. This prevents it from building up and causing problems. Well, that's it for voltage produced by friction. Let's go over what we've said so far. We've talked about the importance of voltage. It's the force that moves electrons along. And we covered 4 ways of producing voltage: by using light, pressure, heat, and friction. Why don't you pause here and look over the material in your text? Take the time to talk over any questions you might have with your instructor, too. We'll be back to cover the last 2 methods, chemical action and magnetism, as soon as you're ready. The 2 ways of producing voltage we're going to cover now are chemical action and magnetism. They're probably the most common methods used today. Let's talk about chemical action first. Chemical action produces voltage in a form we use every day. Batteries use chemical action to produce voltage. Billions of batteries are produced each year to provide power sources for everything from pocket calculators to golf carts. Your plant probably relies on batteries as an emergency source of power and for some of its instrumentation and control systems. The battery in your car is the power source you rely on to start your engine. All batteries are made up of cells. A battery can be composed of one cell or many cells. The battery you see here is made up of 60 individual cells. This cell consists of two plates made of different materials. In this example, one plate is made of zinc and the other one is made of copper. The two plates are surrounded by a solution called an electrolyte, which carries the current. It's usually in the form of a paste or a liquid. The electrolyte in this particular cell is sulfuric acid mixed with water. Chemical action between the plates and the electrolyte causes a negative charge to build up on the zinc plate and a positive charge to build up on the copper plate. Cells are categorized as primary cells or secondary cells. Most primary cells use a moist paste as an electrolyte. You'll often hear a battery that uses a moist paste instead of a liquid electrolyte called a dry cell. Flashlight batteries are dry cells. In this battery, one plate is made of zinc and the other one is carbon. The electrolyte is a paste of starch, flour, and other ingredients. Chemical action between the plates and the electrolyte causes a negative charge to build up on the zinc plate and a positive charge to build on the carbon plate. As a result of this chemical action, the zinc plate slowly dissolves. When the zinc plate is completely dissolved, the cell is dead. It can't provide any more voltage until the zinc plate is replaced. Another way to remember the characteristics of a primary cell is to think of it as a cell that can't be recharged. You wouldn't bother to replace the plate in this battery, you just throw it away. Now, the other type of cell we mentioned, a secondary cell, is just the opposite in that respect. It can be recharged. Sometimes it's called a storage cell for this reason. Take the battery in your car, for instance. If your car won't start in the morning, you can take out your jumper cables, hail another driver, and get enough of a charge from his battery to start your engine. And once you get started, your battery can recharge as you drive. And that's only possible because the battery in your car is made up of secondary cells. This is a typical car battery. It has 6 cells. Each cell has a positive plate and a negative plate. The electrolyte in the cells of this battery is a liquid. Cells that contain liquid electrolyte are often called wet cells. The cells in this battery are connected in series. Each cell, which consists of a positive plate, a negative plate, and a container of electrolyte, produces 2 volts. Because of the way the cells are connected, the voltages produced in each cell are added together to get the total amount of voltage put out by the battery. At 2 volts per cell, that comes to 12 volts in a 6-cell battery. We'll talk more about batteries later on. For right now, let's just keep in mind that it's chemical action that makes a battery work. Now, let's go on to the 6th method on our list, magnetism. Magnetism is the last means of producing voltage that we're going to mention. It's also the most important. You wouldn't be wrong if you went so far as to say that almost all of the electricity used by people is produced using magnetism. Generators use magnetism to convert mechanical energy into electrical energy. Now, earlier we said that electricity is already out there, meaning it's a natural phenomenon. Well, the same is true for magnetism. It's a natural force. And the relationship between magnetism and electricity is important. You'll understand as we get into more detail that electricity and magnetism interact. Why? Well, it has to do with what's known as a magnetic field. As you'll see in a few minutes, whenever current flows through a wire, there's a magnetic field around that wire. Also, if a piece of wire is passed through a magnetic field, magnetism and the mechanical energy required to pass the wire through the magnetic field can produce a voltage that will cause current to flow through the wire. I can demonstrate the relationship between electricity, magnetism, and mechanical energy with the things I've gathered here. Got a magnet, a meter to indicate current with 2 wires connected to it, and a spool. I've wrapped some wire around the spool. Now, in order to do this demonstration, I'm going to have to manipulate a conductor and a magnetic field. To do this, I will move this magnet in and out of the spool. Or I could move the spool up and down the magnet. It doesn't matter which, so long as there's relative motion between them. Now, the motion of the magnet moving through the wire wrapped around the spool is what induces the voltage that causes current to flow through the wire. Next, I'm going to hook these two wires up to the spool. Any reading on the meter now? No. But as soon as I move the magnet, the needle jumps, indicating a current. If I move the spool, same thing happens. We can produce voltage by passing a conductor through a magnetic field. Now, magnetism has a lot to do with how your plant operates. You've got magnetism working for you in generators, in motors, and in relays that keep the equipment going. Okay, we've seen that a magnetic field, together with mechanical energy, can produce a voltage. Now, let's see if current flowing through a wire can create a magnetic field. To find out, we're going to need a circuit and a compass. Now, this needle is pointing toward north because of the Earth's magnetic field, right? And it will continue to indicate north unless it comes in contact with a stronger magnetic field. Well, if what I said about current flowing through a wire causing a magnetic field is true, then we've got a magnetic field right here as soon as I close this circuit. What's the indicator on the compass going to do? Right. It should swing toward the wire. The circuit is closed and the current's flowing. The needle's moving toward the wire. Current flow does create a magnetic field around a wire. Well, we've covered two very important methods of producing voltage: chemical action and magnetism. We'll be going into a lot more detail on these in later units, but let's stop now so that you can think about what you've just seen and review the material in your text. Be sure to take the time to clear up any questions you may have with your instructor before we go on. We've been using electrical terms like circuit, voltage, and current all through this tape. It's hard to talk about a technical subject without using technical terms. So now let's look at these terms a little more closely and at the symbols that go with them. We're also going to talk about some schematics. That's how electrical circuits and components are drawn on paper. And then we'll look at some different types of meters that are used to measure electricity. From this point forward, we'll also be using the term convention. By that we mean a common practice or a commonly held idea that's been around for a long time. We'll be using a simple circuit like this one over and over again as a means of demonstrating how things actually happen. Well, let's start by identifying each of the items on this board. When we use the term circuit, we really mean the path that the current follows. As you know, this circuit is made up of a battery, a light bulb, a switch, and a length of wire to connect them together. A good way to think about the battery in this circuit is to consider it a source, because it's the source of the electricity in the circuit. The battery supplies the voltage or force that causes the electrons to flow. The flow of electrons, as you know, is called current. The symbol for a battery in a schematic looks like this. Now, the light bulb in this circuit can also be thought of in a couple of different ways. Sometimes it's referred to as a load. By load, we mean any device that performs a function when an electric current flows through it. Load can also refer to the amount of electricity being generated. You've probably heard someone ask, what's the load on that generator? Well, what they mean is how much electricity is the generator producing. Any device that is used as a load opposes the current in an electrical circuit. So, in this sense, you can also think of a load as the amount of resistance or opposition to current in a circuit. Resistance interferes with the free flow of electrons and generates heat. In other words, it limits the electron flow to some extent and converts that electrical energy to heat energy. That's how an electric heater works. The symbol for a resistor looks like this. Now, the switch is a simple control device that opens and closes the path for current. It controls the flow. When the switch is closed, the path is complete from the negative terminal to the positive terminal, and current flows. When I open the switch, the path is interrupted, and current stops. This symbol indicates a switch. In fact, the flow of current through this circuit is very similar to the flow of water through a piping system, like this one. It's made up of a pump, a throttle valve, and piping. Let's look at schematics or diagrams of the piping system and the electrical circuit and compare them. The pump corresponds to the battery in terms of its function. The amount of current that flows through the electrical circuit is determined by the amount of voltage coming from the source. The amount of water that flows through the piping system is determined by the pressure coming from the pump. The amount of resistance in the circuit affects the current flow, much the same way that the throttle valve affects the flow of water in the piping system. It limits or controls it. Each of the terms we use to describe the function of the components in this circuit, as well as the components themselves, has a symbol that goes with it. Let's review the old ones and add a few new ones while we're at it. You're probably familiar with most of these symbols already. You may have seen them on the meters in the control room and on the data plates on equipment around the plant. Voltage is represented by the symbol E. The E stands for electromotive force. This force is the result of the difference in potential between a positive charge and a negative charge. The standard unit of measurement for electromotive force, or voltage, is the volt. You use a capital V if you need to abbreviate volts. Current is represented by the symbol I. The standard unit of current is the ampere. An ampere actually refers to the flow of a specific number of electrons. 1 ampere is a flow of a given number of electrons by a given point in 1 second. By the way, that given number is not to be sneezed at. It's 6.25 million electrons. A shorter way to say that is 6.25 times 10 to the 18th power. But even that's a mouthful. Fortunately, we don't have to deal with this number. For our purposes, electric current is always measured in amperes, or as they're commonly referred to, amps. There are a few conventional abbreviations for an ampere. They're capital A, small a, and amp. The symbol for resistance is a capital R. The standard unit of resistance is the ohm. The symbol that's used for ohms is the Greek letter omega. It looks like this. There are some other symbols you'll come across in the schematics you'll be using. A battery is represented this way. The long line indicates the positive terminal, the shorter line indicates the negative terminal. This is the symbol that indicates a resistor. A light bulb looks like this. You remember this. It's the symbol for a switch. We've seen it before. Now, sometimes you can refer to a light bulb in a circuit as a load. We'll be introducing more symbols as we need them, but these will give you a base to build on. Oh, by the way, the conventional means for referring to 2 or more resistors or other components in a schematic is to number them in sequence, R1, R2, R3, for example. To write them, you just place the number just below the symbol and to the right. There are also conventional means for referring to quantities. Here again, we use shortcuts to save time. For example, the prefix mega represents 1 million, and the abbreviation for mega is a capital M. So writing 1 MV, a capital M for mega plus a capital V for volts, is a short way to write 1 million volts. A short way to say 1 million volts is to say 1 megavolt. To express 1 million in mathematical terms, you use the symbol 10 to the 6th power. Kilo is the prefix for 1,000. Its abbreviation is a capital K, so 1,000 volts can be written as 1 kV. 1 kV is 1 kilovolt. In mathematical notation, the symbol for 1,000 is 10 to the 3rd power. Shortcuts are also used in representing very small quantities. The prefix for 1,000th, for example, is milli. The abbreviation for milli is a small m. You can write 1,000th of a volt as 1 MV with a small m. That's 1 millivolt. The mathematical symbol for 1,000th is 10 to the minus 3. The prefix for 1 millionth is micro. The Greek letter mu is the abbreviation for micro, so 1 millionth of a volt is represented by the letter mu plus a capital V for volts. The mathematical symbol for 1 millionth is 10 to the minus 6. You'll need to know what these abbreviations and prefixes mean in order to read the meters in the control room and on equipment all through the plant. You come across several different kinds of meters, too. Some, like voltmeters and ammeters, are designed to measure only one particular quantity. Others, like a multimeter, are designed to measure several different quantities. I'm going to use 3 meters here: a voltmeter, an ammeter, and a meter that measures ohms, to give you an idea of how the meters in your plant measure voltage, current, and resistance. We've used an ammeter before. Then we were only interested in whether the needle moved. But now we're going to find out how much current there is in this circuit. The switch is open, so we can disconnect this wire right here, remove those, and hook up the ammeter. You see, to use an ammeter, you've got to make it part of the circuit. The current you want to measure must pass through the meter. The positive lead goes on this side of the circuit, and the negative lead goes here. Now, there's a name for this kind of connection. It's called a series connection, because all the current that flows through the circuit must pass through the meter. You always set an ammeter up in series with the circuit, otherwise it won't measure all the current. Now, we can close the switch and take a reading. Well, we get around 1¼ amps. So we know that current is flowing through the circuit. Let's open the switch and remove this meter from the circuit. We're going to use the voltmeter next. It's set up differently. It's hooked up in parallel across the circuit. And it makes sense when you figure that voltmeters measure the difference in potential between 2 points. So a voltmeter has to be hooked up between 2 points that you want to measure. Now, voltage doesn't flow through a circuit, so it would be pointless to set it up in series like an ammeter. Now, this is a 6-volt battery, so we should get a reading of about 6 volts. But it might be slightly less. The output of a battery varies depending on how old it is and how much use it gets. Now, we hook positive to positive, and negative to negative, and what do we get? This one reads about 5 volts. It's been used a lot, so that makes sense. Now, the last meter we're going to use can serve several purposes. We have it set so that it functions as an ohm meter to measure resistance. Now, because we're going to take a resistance measurement, we have to de-energize the circuit and disconnect the component we want to test. If we didn't disconnect the component, 2 things could happen. At worst, we'd stand a good chance of damaging the meter, and at best, we'd get an inaccurate reading because the meter might pick up resistance from other components. Well, instead of testing the resistance of the light bulb, which might vary because of age or amount of use, for example, we're going to test these resistors. A resistor is just a device with a known fixed resistance. They oppose current flow just like the light bulb, but with these resistors, we get a more accurate measurement. Each is rated at a value of 12 ohms. Now, I will place a probe on each side. And this one reads about 12 ohms, 12. And this one, whoops, 11.9 or 12, well within the tolerance. And same for this. By the way, if you need to jot down the resistance of each of these resistors, you do it this way. What do you think would happen if we connected these resistors together in series and then tested them? Well, let's put them all in place here. Then we'll do. And the meter reads 35.8 ohms. That tells us that when resistors are connected in series, the individual values added together equal the total, just as the voltage is added up when we connected a pair of batteries in series. Well, we've covered a lot of ground in this segment. We've talked about simple circuits, electrical terms and symbols, and units of measure. And we've looked at a few meters and how to use them. Why don't you take some time to review this material in your text before we go on, and make sure all of your questions get answered too. That's why the instructor's there. In this segment, we're going to talk about the relationship between voltage, current, and resistance. A man named George Simon Ohm entered the Electrical Hall of Fame when he discovered that relationship. He said that in an electrical circuit, the current is directly proportional to the voltage and inversely proportional to the resistance. You might have heard Ohm's law stated a little differently. Current equals voltage divided by resistance. Perhaps you've seen it represented like this: I equals E over R, or like this. But regardless of whether or not you've seen it before, it's very helpful in understanding how electricity works and how your plant uses it. According to Ohm's law, a change in one electrical property affects one or both of the others. This law will help you to understand how the properties of electricity interact. The water flow through that piping system we saw earlier is affected by the pump and the valve in much the same way that current is affected by voltage and resistance. If I increase the pressure from the pump, water flows through the piping at a faster rate and more water is pumped. That is, if the valve remains in the same position. It's the same with electricity. If the resistance stays the same, increased voltage means increased current. On the other hand, if the amount of force from the pump remains the same, I can control the flow by how much I open or close the valve. By varying the resistance in the circuit, I can directly control the flow of current with a constant voltage. Now, let's use the circuit board and the meters again and see what we can do about proving Ohm's law by working it out with real components. We said that current is directly proportional to voltage. To check that out, we need to take two current readings on this circuit. First, though, let's see what our voltage is. We connect positive to positive. And we connect negative to negative. Okay? It's 12 volts. Now, keep this fella together here. Our first current reading with this voltage, and we already have our ammeter connected. The current is flowing through the ammeter. Our first current reading with this voltage is 2 amps, which we see when we activate the switch. Now, we'll change the circuit by adding another battery in series with the first one. The rating on this battery is 12 volts, so we are adding 12 more volts to the circuit. Now notice that we aren't changing the other component, the light bulb. It'll be the same in both circuits, so the value of the resistance in both cases stays the same. Now the ammeter's hooked up in series, just as it should be. Now I'll bring in the second 12-volt battery. This is the negative right here. Which is a bit pesky. There it is. Now, we close the switch, and the meter reads 4 amps. Well, that tells us that as voltage increases, current increases as long as resistance doesn't change. In this case, when we doubled the voltage, the current also doubled. By the way, the light got brighter, didn't it? Well, that's another indication that current flow increased. Next, we'll check it out the opposite way. We'll decrease the voltage. Now, we have already de-energized the circuit over here by opening the switch. What we're going to do is put a 6-volt battery into the circuit, and we will check it against our original reading of 2 amps. We connect the positive and the negative. The value of the resistance stays the same, just as before. I close the switch. What do we get? 1 amp. So it checks out. With half as much voltage, we got half as much current. Current is directly proportional to voltage. When the voltage was doubled in the first example, the current doubled. When we halved the voltage in the second example, current decreased by half. Now remember, the resistance remained constant in each case. Now that we've seen the relationship between current and voltage when resistance is constant, we can use a simple formula to predict what current should be for specific values of voltage and resistance. You'll find this helpful later when we get to talk about series and parallel circuits and about how your plant is wired. Earlier, we said that you might have seen Ohm's law represented by a circle with some letters in it, like this. The E stands for voltage, or volts. The I stands for current, or amps, and the R stands for resistance, ohms. Right now, we want to figure some current values, so we cover the I and we get E over R. Well, let's put in some numbers and see if it works. The light bulb in our circuit has a resistance of 6 ohms. The batteries we're using each supply 12 volts. So, to find out how much current we should have in a circuit with one battery, we set up the formula like this. I equals E over R. So I equals 12 over 6. I equals 2 amps. If we double the voltage, that is, if we have 2 batteries connected in series, we also double the current, like this. I equals 24 over 6, or I equals 4 amps. Now, if we cut the voltage in half, we can use the formula to show that we will get half as much current. As we have been saying, current is directly proportional to voltage, as long as resistance doesn't change. The next factor in Ohm's law that we're going to check out is resistance. Resistance is a physical property. It's not a rate of flow or a difference in potential. Under ordinary circumstances, the value of a resistor doesn't change. If you want to change the amount of resistance in a circuit, you usually just put more in or take some out. You can control the amount of current in a circuit by using devices with different values of resistance. Ohm's law says that current is inversely proportional to the resistance in a circuit. This means that when resistance increases, current decreases, and vice versa. When resistance is decreased, current increases. But for this to happen, voltage must be fixed. Now first we're going to determine how much current is flowing through the circuit. Then we'll add another light bulb in series and see what we get. First though, I'm going to give us a larger battery to do this job. 12-volt battery. Now the meter is already hooked up, so we'll close the switch. We get 2 amps. Now, if we add another light bulb, we should get a lower reading because we're increasing the resistance. Okay, we connect the light bulb this way so that the current flows from negative through the meter, through the new light bulb, through the old light bulb, into the switch, back to the positive right here. Switch is open and the light bulb is in. Now when we close the switch, the reading is 1 amp. It worked out. Not only is there less current going through the meter, but the light from the 2 bulbs is dimmer than the light from the single bulb. And that's another indication that the current has been reduced. So we can figure that resistances hooked up in series add up. We can also assume that if the voltage remains constant, the greater resistance we have in the circuit, the lower the current flow will be, and vice versa. We can go back to the formula we used earlier to show how current and resistance affect each other when voltage is constant. According to Ohm's law, current equals voltage divided by resistance. I equals E divided by R. So, if our circuit has a 12-volt battery and 1 light bulb with a resistance of 6 ohms, the current should be 2 amps. If we add another light bulb in series, the resistance increases to 12 ohms and the current decreases to about 1 amp. We have the formula I equals E divided by R. So I equals 12 divided by 6, or 2 amps. And then I equals 12 divided by 12, or 1 amp. Now the readings that you might get during an experiment are not always the exact values that you get by working out the formulas. As you've seen, batteries do not always produce the exact voltages that they should because they're affected by factors like age and amount of use. Light bulbs are also not very accurate resistors. You'll come closer to your predictions if you use resistors with fixed, known resistances. We've shown you how to represent Ohm's law as a formula for figuring out what current should be. We can also rearrange the formula to figure out what either voltage or resistance should be when the other 2 values are known. Going back to the circle, you can see that we can find voltage by covering up the E. E equals I times R. We can find resistances by covering up the R. R equals E divided by I. Let's look at the voltage formulas first. If we have a circuit with a known resistance of 5 ohms and we get a current reading of 2.4 amps, we can figure out the voltage like this. E equals I times R. Or E equals, in this case, 2.4 times 5, or 12 volts. And if we know what current and voltage are, we can calculate the resistance. For instance, if we know that our circuit contains a 12-volt battery and we get a current reading of 2.4 amps, we can figure out the resistance. Formula is R equals E divided by I. So it's R equals 12 divided by 2.4, or 5 ohms. You'll find more exercises like this in your text. Be sure to take the time to work them out. The practice will help you to become more comfortable with the relationship between current, voltage, and resistance. Now, before we leave our old friend, the circuit board, I wanted to mention two more things: open circuits and short circuits. Both of these interfere with the normal flow of electricity. We've already talked about an open circuit. If we open the switch on our circuit board and take a reading on the ammeter, you'll see it in practice. Air offers maximum resistance to the flow of current, so there should be no reading on the ammeter, and there isn't. Current can't flow in an open circuit. A short circuit occurs when the resistance in a circuit drops to near zero. We know that current increases when resistance decreases as long as voltage is constant. So minimum resistance means maximum current flow. This maximum current can be dangerous. It can damage circuits and start fires because of the intense heat it produces. Well, we've covered a lot of material in this unit. We started with the properties of the electron and how and why electrons flow, and then we looked at 6 common ways to produce voltage and some frequently used electrical terms and symbols. We saw how current, voltage, and resistance are related. And we did some exercises using Ohm's law. We've only talked about DC current so far, but AC is coming up soon. You're going to need to know what we've covered here in order to understand what comes next. So read over the material in your text now and discuss any questions you have with your instructor and other members of the class. As an operator, you need to be on top of things all the time. Be sure to build a good, solid foundation for yourself starting now.